Good morning. Welcome to another episode of XR Talk Show. Today's topic is I don't know yet. So today's topic is actually you go here, you go to XR programming blog, which is this URL. You can just search for XR programming blog. And then there is a list of topics like this. This is my programming blog list of topics, and just comment in the box here and let me know what you want me to talk about. So let's pop out this window. There is a pop out chat. That's good. Okay, but this window it doesn't show how many people are watching. Okay, while I'm waiting for people, let's just let me just go to here, see list of topics, type 1 in the chat box, and I'll talk about it. Actually, let me begin by I got work to do. Hey guys, say something. So let me begin by I'm going to let's go to my Python blog, my Python tutorial, and you see most of these are Python 2. You can see, for example, string methods. Not this one. Okay, so let's see format string. You can see the code is Python 2 because because the print statement they don't have parentheses. And this tutorial began in 2005, but I have written also Python 3, but the topic are not many. But basically Python 2 and Python 3 are very similar, so it's kind of redundant to have them separate. And I've been thinking whether I should separate them or put them together, like adjacent, like one page covers both. And I think now is a good time to put them both one by one. I mean merge them together into one. And essentially the plan is I'll just cover the main thing will be Python 3, then with footnote that discuss in this case, okay, if you are using Python 2, then you do the other way. So I'm gonna talk about that. And hi guys, say something, type something. So okay, let's start with the Python then. So this is my HTML, this is my code. Let me show you an example of what to do, what I'm doing. So I'm using XR HTML mod. So let's start XR start command log mod. And on the left window here, you can see all emacs commands I'm calling. For example, if I move cursor, you'll see the command, everything. And so this HTML page showing browser, and we got that's Python 2 code. Now look, let's go to here and I press a button. That's XR get precode make new file. Kind of a long name. So now we have, it just actually pulled the code into a new buffer and put it in Python mod. And actually, I can run this, run it. So the result is, what is this? Let's try it again. Yeah, I get that message. Now, I've got this message before. I'm not sure why it's happening. Alarm clock 14. Why is that? Anyway, so I can run the code, run it, and you see here's the result. 14916. But this is Python 2 code. I need to change it to Python 3. So in order to do that, let's put it, let's move it down. Let's put the parentheses. Then, oh, and let's change the file name to py3. You know, Python is stupid. You know, they refuse to create an extension for Python 3. And that actually creates a problem because, you know, because Python 2 and Python 3 are not compatible. You know, so if you have the same extension, it doesn't really work. You cannot determine, you know, then you have to put, you know, what version it is, you know, as a comment, something like that, or use the shebang, which is has been phased out basically. But anyway, you put you put you know what I mean by shebang. Shebang is a Unix philosophy shit, you know, like that, like this user being Python, you know, basically the first line is special. Not just the first line, actually the first character, you know, it the Unix treats the first character differently. So the first line, it's the path to the executable, then you'll use that to run the file. That's called shebang. Okay, that's called let me show you, this is called shebang. Yeah, you know, the Unix people have these jargons, and back then it's all very popular. Everyone is you know, all these jargons, cat and so on, tail, head. But anyway, so you run this, you got, oh, you see, this is actually, this is Python 3 code, because it, you know, map doesn't return a list anymore. It returns a blob. It returns a abstract blob. I hate that. It's stupid, you know, these Python people. Yeah, but they have a reason, of course. The reason is that, you know, it's inefficient to actually create a list. Suppose you have a billion items. You know, you want to create a list of 1 to a billion. And if you use, you know, map, you're gonna have a billion items. So they, or range, you know, they decided, you know, they wanted to abstract it. So they created this, what is this called? Thing, where, you know, it's kind of like lazy evaluation, but not really. Basically, if you don't access the elements, it's not generated. It's generated only when you access the element. What is it called? Anyone know? Hey Norman, good morning. Where are you at? Or is it afternoon or evening or night? So what should I talk about today? So, you know, go here. Okay, so let me put the stuff here. I don't know if this will work, but let's try it. So today's topic is going to be, well, today's date is going to be Saw Talk Show 17. Okay. So wait for a few seconds. It should update, and let me know if you actually see this in the, you know, YouTube below the you know, the info section. Iterator, yeah. No, no, it's not East Coast time. Oh, okay. So it's 2 o'clock for you, 2 p.m. No, it's not iterators. They call it. Let's see. I'll find it. So Python 2 and Python 3 differences. Map returns. Oh, you are right. Iterators. Okay. Yeah, they read. You know, iterators. Iterators. Yeah, you are right. So generator. Yeah, generator. Yeah, I don't like those things? Do you like those things? Well, apparently a lot of people do, especially especially the object-oriented programming. Those people like that. Well, they like it because because the OOP languages are very limited. They cannot express much. So that is the only way for them, to do that. Iterators and generators. Yeah, I despise them. They are now in JavaScript as well, Python and JavaScript. You don't find those in functional languages in general. Not in Lisp, not in well in Haskell. I don't know about Haskell. Yeah, I'm not sure, but Haskell has least comprehension, which is another idiocy. The thing about the functional programming is that functional programming is great, but typically in any field you have when something become popular, you have a fashionable crowd. So this crowd, because it's very popular, so you have a lot of people, and so in general the quality, the knowledge, they don't know things, but however they are enthusiastic about the subject. So they try to talk about things, but they don't actually know stuff. you know so which is today's situation for Haskell. You got lots of these Haskell coders. They tell you about monads and stuff, but they know like zero mathematics. They don't know what's basic math, algebra or group theory. But every day they are like, oh, category theory, oh, monad, oh, referential transparency. Like that's the situation. So Python map to this generator. So anyway, so here's to a good life, to mathematics. Are you married? So can anyone see the topics here? Like I just posted a list of topics in I suppose below your video window. Hi, uh, Domingo, Domingo. Okay, should it be Domingo Gomez? Ooh, this is brandy. My roommate's cheap brandy. Hey Dion, great to see you. So I'm wondering, what should I talk today? Oh, you can see the topic. Great. So just type something and let me know the topic. What to talk about. I was thinking, I should do a non-technical topic, because non-technical, then it's kind of wide range of topics. Yeah, wide range. Like yeah, that's what the normal talk show is about. My talk show is like nerds talk show. The programming, math, and stuff. But the general talk show is like they talk about politics. And Joe Rogan, Joe Rogan's talk show. He's every time he invite guests, and he's drinking and smoking weed and stuff. Ooh. Okay, math, group theory and symmetry and wallpaper groups. That's a great topic. A Dinesh. Oh my God, the names are so difficult to pronounce. Well, partly because English. English. There's a term for that for in linguistics, where when you have a language where the writing system, for example, if you have a phonetic alphabet, not necessarily so. I mean, even let's say English, where the pronunciation corresponds to the written, the alphabet. There's that property. There's a name for that property. I forgot what it is. But anyway, Spanish is very much like that. It's like there's a spectrum. So Spanish is very much like that. The pronunciation corresponds to how it's written. Of course, in artificial languages, constructed languages such as Lojbang and Esperanto, it's 100% regular. The pronunciation corresponds to how it's written. But in English, it's very bad. So a Danesh or Dinesh, or I could spell Dinesh. Okay, I already forgot what's my first. Um, well, anyway, so let's talk about then group theory. Oh my God, such a tough subject. Okay, I hope I'm not drunk. It's Dinesh. Dinesh. Okay, I think it's Dinesh. Okay, groups. Yeah. Okay, I hope I can pull it off. By that I mean I can, so the topic is group theory. So I'm going to give you guys a introduction to group theory, and I hope that I can express the way I wanted to, meaning that I can teach you the subject to my own satisfaction. Like, if you know some subjects such as programming, you have a lot of opinions, and you also have opinions of how to teach it. Sometimes you see other people teaching it, you think it's wrong because they don't convey the idea, or they are wrong in some other way. They are misleading, maybe that. So usually when you know something well, you have like your opinion about teaching it. So I do have opinions about teaching math and group theory. So I hope to I'll be able to convey to you, teach you the way I want, and also, of course, also that you actually understand and grasp the subject well, to such a degree that from today on you are going to love mathematics. Okay, here's the question: does group theory have important application in comp sci? Practically speaking, no, zero. Well, it's kind of fuzzy. I mean, it's kind of hard to say. I mean, if you say, I mean, in one sense, every mathematics has fundamental application in computer science. In fact, computer science is just math. Okay, well, you have, yeah, computer science. If you dig into the heart of computer science, it's all just math. It involves number theory, for example, computer science, we talk about cryptography. That's actually just number theory, and many other very highly advanced math, such as projective geometry, rational curves, and things like that. Those subjects you have to study, for like 5 years of math. You have like to have a master's degree in math or PhD to actually begin to understand it. We're not talking about research yet. We're not talking about trying to study, find out what's new, or what. You take 5 years to actually to understand what they are talking about, understand the subject, like cryptography, number theory, and so on. And also group theory. So what is group theory? It is one of the, you can say it is the most fundamental of all math. Okay, in many math subjects, everyone, almost like when you study math, almost every subject, every book, the author will say this is one of the most important. After you read that, for a while, you get confused. So just exactly which one is the most important, But anyway, so in general, math you can divide into like two sub kind of categorization. So you have algebra on one hand, and the other side is analysis, which is calculus. Okay, analysis in algebra. So analysis studies continuous functions, limit. Basically everything is smooth, and study infinity and infinitesimal, like infinitely small. So yeah, if you haven't studied calculus, you might wonder what do they how, I mean, what possibly things you can study of infinity. But yeah, anyway, that's calculus analysis. On the other side is algebra. Now algebra is about structure. It's about structure. It's hard to explain until you actually get into the math. So I'm going to talk about group theory. So algebra. So there's algebra. Then there's calculus. Calculus is about as far as application goes, you can measure the speed of a car. That's actually calculus. You can measure the area of some swimming pool, irregular shaped swimming pool, things like that. Of course, it's far more deeper than that, and fractals and and, too many things. So anyway, so two major categories: analysis, sometimes called calculus, depending on your country, and the other one is algebra. Algebra is all about structures. It's about okay, yeah, yeah. You have to actually start to. I have to start to talk about it in order to show what it is. So I'm going to talk about group theory. Now, group theory. Okay, here's what I can say. Group theory is the most basic, the most fundamental thing you study in algebra. So in other words, okay, so we have analysis, we have algebra. For every mathematician, doesn't matter which field, any mathematician, when you study undergraduate math major, you have to know the basics of both. Yeah, because I mean you have to know basic of both in order to go anywhere. I mean, so you have to know basic of both. So for the algebra, the basic of the most basic of the algebra is group theory. Okay, well, some people might say it's linear algebra, but actually, group theory is the algebra proper. Okay, so that's how important it is. And in fact, every math field, every math, I really mean every, like 100%, or 99.9999% of math in any math field, you have to understand group theory. I mean, group theory is just like it's like alphabet in English. You have to know it. So that's how important it is. But okay, so I'm going to try to talk about group theory. I need another drink. Okay, so group theory. So let me begin by saying, okay, group. Um, let me, yeah, okay. So you know about symmetry, the word symmetry. Now there are many aspects of group theory. Okay, there are many approaches. It's just like like in philosophies, or in economics. Some books will start by what is economics, or what is philosophy, or what is mathematics. There are tons of books written about those things, or sometimes in English, maybe, oh yeah, what is programming? In programming, in some books you'll see, they start by, there's a chapter, what is programming. So different author always have like different philosophy, like they try to tell you what is mathematics, but usually they are, it's kind of first, it's just very different. So I'm going to give you my perspective of what is group theory. So let me show. Okay, so you know about symmetry, the word, the English word symmetry. So for example, if you look at my face, I'm symmetric. It's called bilateral symmetry. Any human animal, if you are healthy, average, you have eyes on each side, you have hands on each side. It's symmetric. So if you can, you can flip a person, left, right. It's the same. Or for example, the bilateral symmetry. So let's say A, B, C, D, E, F, G, H, I. Okay? Now, A is symmetric. It's bilateral symmetry because there's a vertical line. You flipped it, it's still A. B is symmetric. It's also bilateral symmetry. There's a horizontal line. You can flip it, it's the same. And similarly for C, D, E, H is more interesting. It's yes, it's bilateral symmetry. It has two bilateral symmetries. That's the way we say it, because there's a horizontal line. There's also a vertical line. But however, in fact, it also has a rotational symmetry. That is, you rotate the edge, 180 degrees. It's edge again. Now that is not the case for A, not the case for B, not the case for C. Unless you do another flip. But that's another thing. So anyway, we have all these symmetry, and we have the O. Suppose it's perfectly round, then that's a rotational symmetry. That's infinite rotational symmetry. So let me show some example. Let's say so okay, anyway, so these are ideas of symmetry. Now let me talk about something else. Okay, let's see this. A cup. You see, this is my mug for my energy drink or tea or coffee. So this thing's got symmetry. Again, the symmetry is bilateral symmetry. So you imagine there's a plane, and it's symmetric around that plane. And okay, symmetry. What else? Symmetry. I'm trying to give you some examples of symmetry, but I guess I suppose you get idea. But this is important because this is all group theory is about. The entire group theory is about symmetry. Okay, this is very interesting. Yeah, I want to give you some other examples. Let's see. I mean, because we are going to starting to get deep. Let's see, regular polygon. Let's do that. Actually, let's go to my website. Yeah, Xali website. It's got everything. The encyclopedia of the world. Xali.info. And you go to math. Then you go to wallpaper groups. Then you go to, hi guys. So today I'm talking about symmetry, math subject, group theory. Okay, so I have written this article, but I don't, the one thing you don't want to do, I don't want to do, is to when doing a lecture or a video presentation, you begin to like read off a book, because whenever you have a page there, people start to read it, so they have attention bifurcation. Like on one hand, they're trying to read it. On one hand, you are talking. They're trying to listen to you, so they got distracted. So I think the best. So there are many styles of presentation, but for me, I want to avoid, showing the material, the slides. But basically, I'm here only to show you some pictures. I want to get some pictures about. Well, let's not. Let's go to regular polygon. What I'm doing is I want to show you some symmetries. Let's see. Google.com. I want to do things fast because I don't want to waste your guys' time, because I'm a workaholic. Every time I talk, I have to do something. Never mind. Okay, let's look at the cube. So we got many pictures of cube. You can see there's many symmetries here. You see this cube, you have a plane over here. You have like 3 planes, orthogonal planes. You have 3 planes that's symmetric. You flip the cube, then it's still a cube. That's what symmetry means. That means it almost means like if you just have part of it, you can generate the whole picture, the whole thing. That's what symmetry means. So cube, you have many symmetries. You have planes, and you also have rotational symmetry. And that means you take this cube, you rotate it 90 degrees, it's again the same thing. And you can rotate it again, that's the same thing. So you got 90-degree rotational symmetry over one axis, and you also got 180-degree rotational symmetry. Uh, but that's not all, because there's another axis, on the side, going horizontally, that also serves as a rotational symmetry axis. So you rotate, you can rotate the cube in many ways, and it come back to itself. That is symmetry. Okay. So let's show some others. So let's see cube. Okay, let's see pyramid. You also got rotational symmetry. In this case, what symmetries are there? Okay, so your task is to analyze any object. Okay, in your daily life, you look at any object and analyze it. You want to find all possible symmetries. So what do we have in a pyramid? Okay, we have a plane. That gives us a mirror symmetry. We have another plane that gives us symmetry. And also we have a rotational symmetry over a vertical axis. Yeah, yin yang symbol has a rotational symmetry. Okay, so these are symmetries. So far, we have discovered, let's say, we have discovered several types of symmetries. We have for example, face bilateral symmetry. In math, we call that we don't call bilateral, but we call it a mirror symmetry. Okay, so it's like a mirror. You flipped it, so it's called mirror symmetry. So we have mirror symmetry, we have rotational symmetry. Um, let me show you. That's it. Okay, let's not get over too much. There are other type of symmetries, but let's not cover it now. But so we just have now we have mirror symmetry. Mirror symmetry is over a line in 2 dimensions. For example, a square. You have a line in the middle that you flip the square, it's the same thing. So that's a mirror symmetry. But in three dimensional, if you have a cube, you have a cup, then the mirror symmetry is a plane. You flipped it kind of inside out, and it's still the cup. So you got mirror symmetry in 2 dimensions or 3 dimensions. You got rotational symmetry in 2 dimensional or 3 dimensional or 3 dimensional. 2 dimensional symmetry is like yin yang symbol or Z. That's right. So Z is a good example. Z has it does okay. So ask yourself, does it has mirror symmetry? Does the letter Z have mirror symmetry? The answer is no. However, it has rotational symmetry. You rotate it around the center 180 degrees, it becomes itself. So that's rotational symmetry. Now that's 2 dimensional because all the letters are 2 dimensional. But in 3 dimensions, we in 3 dimensions, what's a good example? Let's see. God, I don't have a thing for 3 dimensional rotate. We want a example of 3 dimensional rotational symmetry, and hopefully not anything else. There's no mirror symmetry of the subject, but except the only symmetry of the thing is a rotational symmetry. So can you guys think of a thing, a 3 dimensional object that has rotational symmetry? Now, obviously, a pyramid, has it, because a pyramid, you rotate it 90 degrees along a vertical axis, then it becomes itself. But however, a pyramid also has a mirror symmetry. So, but we are trying to find a object that does not have mirror symmetry that only have rotational symmetry. So anyone? Okay, I got an example. Let me show you. Cogwheel. Okay, we got several cogwheels, but these are not what I'm looking for. Do you know why? Because, for example, if you look at this cogwheel, yes, it has rotational symmetry. You rotate it a little bit, it becomes itself. However, it also has many mirror symmetries, around the lines. But I'm trying to find a cogwheel that only has rotational symmetry and do not have mirror symmetry. Okay, I'm getting too complicated, but I'll tell you what example. I'll tell you right away. Except, uh, let's see. You might be wondering, why am I spending all this time about symmetry? And just get on with the group theory. But this is fundamental in getting warming up, because group theory is all about symmetry. Group theory is the study of symmetry, period. So that is very interesting. So how possibly, what possible things can you study about symmetry? I mean, it's just okay, it's just shapes. uh, there it is. Finally I found one. You see this thing here, this twisted wheel. Now that this twisted cogwheel, that has rotational symmetry. Obviously you rotate it a little bit, it becomes itself. However, it does not have mirror symmetry. There's no plane where you flipped it, it becomes itself. Well, it'll become like the opposite orientation, but that's another thing. So you get what I'm saying, right? In two dimensions. Okay, so this is a three-dimensional example of a object that has rotational symmetry but do not have any mirror symmetry. This is one example, especially this one, more pronounced, this one. Okay, but let me show you a two-dimensional example. Two-dimensional example is pretty easy to find. If you look here, you'll find it. There. Okay. Well, sad to say, but all these are examples of a two-dimensional object that has rotational symmetry but do not have mirror symmetry. Now, by the way, if you don't know what these origin. These symbols are ancient, from maybe 3,000 years ago. The origin of these are Buddhist symbols, and in fact, you can see. And I'm not gonna go into that, but anyway, these are Buddhism symbols. Okay. Uh, in fact, in this character in Chinese is pronounced one, one, like WAN. That's the pronunciation of this character. It's not a character you see every day, though. I mean, it's from the Buddhist script. Uh, I mean, the origin is from India. India is the origin of Buddhism. So anyway, so that's an example of symmetry that has rotational symmetry but no mirror symmetry. Oh, actually, Z is a good example. I forgot Z right here. Z, as the Canadian like to say, Z. So okay, okay, we talked about symmetry a lot, so we know there are different types: rotational and mirror symmetry. and it can be two-dimensional or three-dimensional. Now let's okay. One more thing about symmetry. Then we'll start the group theory. Because once I talk about symmetry, once you know these things, then when I talk about group theory, you kind of get it. Because it sets up the it warms you up. It sets up the environment. Okay, so let's look at the most fascinating object of programmers. The most popular subject of math among programmers, which is polyhedra. There it is. Let's look at Wikipedia. There are so many symmetries there. Okay, so you can see these are polyhedra. You've probably seen thousands of them, especially among programmers. Like you might already have written a program to draw them. So let's look at some examples. Okay, so well, let's just look at these. These are all polyhedras. Uh, let's just go to, these are too complicated. Let's simplify. Let's go to platonic solids. Okay, here's a good picture. Okay, these five are called platonic solids, and this is a picture in real life. One, two, three, four. What? Yeah, those are not. Why they put it there? Shit, stupid people. So anyway, these are platonic solids. Uh, let's talk about symmetry. You know, so your job is to, let's look at this one, the dodecahedron. Your job is to identify all the symmetries. What symmetries are there? For example, we know two types, right? We know rotational symmetry and we know mirror symmetry. Now this thing obviously has lots of it. There are so many planes that um, that that it is a symmetric plane for this object, and also there are many rotational symmetries. Okay, so okay, let's get down to groups. I think I've been talking too much, like 42 minutes. Oh my god. Okay, so that's it about symmetry. Okay, so we know enough about that. So group theory is the study of symmetry. So now imagine, now you are a programmer, right? You are a programmer, and in programming we write functions, we have parameters. Like in real world, if you are programming for a company or whatever, you write programs. Usually you want to capture the different possibilities by the parameter of a function. Suppose the function does something, and the parameters can capture different possibilities. In other words, you encode a problem in real life into a function's parameters. So all the possibilities are encoded. All the possible variations can be expressed by the parameters of the function. You call the function with the different parameters. You cover all the situations you need. So your job now is, given any 3D object that has rotational symmetry and mirror symmetry, you want to codify it. So in other words, let me give you an example. This cube has many different symmetries. You have three mirror planes, and you have one, two, three rotational axes. Each one has the axis. Each one has a rotational symmetry, and the plane has mirror symmetry. Now, for the tetrahedron, you also have like one, two, three, four rotational axes, and four. Wait, one, two, yeah, four mirror planes. So, but obviously, cube and tetrahedron are different. I mean, their symmetry are different. So your job is to come up with a string, a sequence of code, A C C B A or something that captures the symmetry. That is, a string of symbols that when you look at this sequence of symbols, then it's the symmetry is a cube. Um, let's see. When you have a symmetry, let's say a cup again. This is a 3D object. It has only one symmetry, a mirror symmetry, and that's the only symmetry it has, only one. Now let's look at another cup. This cup is a different cup. However, it also has one symmetry, just a mirror plane. So these two cups have the same symmetry, even the object is entirely different. In the same way, if you have an object that has the same symmetry as a cube, I mean, you can have many different shapes, but however, that thing has the same symmetry as a cube. For example, you can extend, each face of the cube a little bit, make it like a little pyramid. However, the whole thing, the symmetry is still a cube. So anyway, your job is to come up with a code. So that code codify. In math we say codify. Identify, codify the symmetry, capture. So whenever people see that string, they know is this the symmetry of the cube. So anyway, each this object, for example, they have different set of symmetries, and there is a code for them. It captures them. So let me just say, each there is not a group, is a abstract idea, okay, and just like a set. A set is an abstract idea in math. In math, you can have many different sets. You can have a set of people, a set of numbers, a set of stones, anything. In the same way, a group is a set with one operation and some restrictions. We'll get into that. But anyway, there are many groups. Just like said, there's many groups. So what I'm saying is that each one of these symmetries, remember, not the object, not the cube, octahedron, dodecahedron, and so on. The symmetry of the object, each one of them is a group. So there is a group called cube symmetry group. Actually, that's not the name they use, but I don't remember the name. But there's a group with a specific name that is a cube symmetry group. There is another group that is the octahedron symmetry group, and so on, for the same thing for dodecahedron and isocahedron. In fact, all possible set of symmetries that are finite is a group. And in fact, mathematicians has classified, this is a huge task, okay, mathematicians about 30 years ago, they have found and classified, categorized all possible finite groups. Okay, let's see, let's just search for all possible finite groups. Okay, finite group. There's a so it's a this is a big. This is another chapter in mathematics. I mean, by chapter I mean it's a huge milestone. Yeah, mathematicians has classified all possible finite groups. Now we are talking about finite groups because there are infinite groups as well, meaning that the group has infinite number of symmetries. What is an example? Here is an example. Can you see? There are infinite number of symmetries of a ball because first of all it has a mirror symmetry, but on any plane, like any way you cut it, it's a mirror symmetry. So there's an infinite number of mirror symmetry planes, and also it has an infinite number of rotational symmetry. Like you rotate the ball in the center, from its center. Doesn't matter how much degree or in what direction, it's still the ball. It doesn't change. So the symmetry of a ball is a infinite group. In fact, that group is called cyclic group. So you see, we are beginning to see the different groups. I mean, even I haven't began to give you the definition or meaning of it, but you already begin to see the nature of groups. What it is about. I mean, you already understand the fundamental nature of the group. So let's look at the cyclic group. CYCLIC group. Now, cyclic group is one particular group that is basically the group of a circle. Now, a circle is also infinite symmetry. That's for two-dimensional. So there it is, cyclic group. So let me read it a little bit because cyclic group is one of the most fundamental group. Let me read it about it a little bit. So in group theory, a branch of abstract algebra, a cyclic group, or also called monogeneous group. Now, nobody calls that. So a cyclic group is a group that is generated by a single element. That is, it is a set of invertible elements with a single associative binary operation, and it contains an element G such that every other element of the group may be obtained by repeatedly applying the group operations to G or its inverse. Yeah, that's a cyclic group. Okay, so I mean, you can read about it. I hope that gives you the talk about symmetry gives you the essential idea to, when you read this, you'll now understand much more. Now let's get back to, maybe we should talk about the definition of symmetry of the group. So a group is a okay, from pure mathematical point of view. I mean, of course, group is a math object subject. So a group is two things. I mean, group is made of two things. One, a set of things. Anything, a set, and operation. Operation just means a function. Okay, a binary operation. You can think of as a function with two arguments. So now, what does the function do? The function takes any two elements in a group and returns any other elements in a group. That is what the function do. It's called binary operation. By tradition, it's called binary operation. So you take any two elements in a group, then you apply the binary operation. Usually, it's written as it may be written as a plus sign or multiplication, or even omit entirely. But you can think of it as just like a multiplication. So you take any two elements in a group, and it returns another elements in a group. So a group is a set and an operation, a binary operation. However, the binary operation must satisfy some qualifications, some rules. So let's look at what are those rules. Finite group. Let's see. Let's find the definition of a group. Okay, here is some like introductory discussion about groups, so you can read about it in Wikipedia. Uh, so it tries to give you some illustrations, definition. Okay, so here's a definition. A group is a set G together with an operation that combines any two elements A and B to form another element, denoted A dot B or AB. To qualify as a group, uh, the set and the operation must satisfy four requirements known as the group axioms. So first one, closure. For all A, B in G, the result of operation A dot B is also in G. Yeah, of course. Uh, and associativity. For A and B and C in G, then A dot B then dot C equals to A dot B dot C first. Okay, that's just a rule. Okay, this rule is called associativity. Now, it may appear to you that this is odd. Like, why do they give that definition? But I would say just don't worry about it. I mean, if you already know the topic, you can look up. I have an article about that. Xali associativity. The nature of associative property of algebra. Now, if you are curious about associativity, you can read this article. So let's go back to group definition. So you need closure, you need associativity, you need identity element. So there exists an element E in G such that for every element A in G, the equation E dot A equals to A dot E equals to A hold. So that means I mean, like the article said, there in your group, if you apply the binary operation, two elements in a group, there must exist an element such that that element dot any uh, that element dot another element is equals to the another element itself. That meaning that you have this element in the group, we call it identity element, such that when you apply the binary operation of it and any other element, the result is the other element. It's like zero when you do addition. 5 plus 0 is still 5. 10 plus 0 is still 10. 9 plus 0 is still 9. Or you can think of it as a 1, the number 1 in multiplication. So 5 times 1 is still 5. 9 times 1 is still 9. So 1, the number 1 is called the identity element with respect to multiplication. The number 0 is the identity element with respect to addition. So you get the idea. So in group theory, it requires you to have something similar. It requires you to have an element such that when you apply that binary operation, it just returns the other thing. And then there's an inverse element. Okay, how long I've been talking? 1 hour. That's about right. We about doing great. Okay, so any questions? Am I doing okay? I mean, well, am I too verbose? Maybe I should cut down on that. In my talk show, am I too verbose? Like, are you guys, like going off? Some people when they listen to a podcast or video, they don't actually watch. Maybe they are doing some kitchen work, or they are doing something with their kids or something, or maybe driving, so they don't necessarily watch. So I try to always, I learn from watching other videos, and you want to like read things and keep talking. Great, thank you, Dion. So So anyway, so you require, the operation requires these four elements. There's also an inverse element. So it says for each A in G there exists an element B in G, commonly denoted, blah blah blah, such that A dot B equals to B dot A equals to E. So here's the important part. A dot B, so there must have an element, so for any element in your group, you pick anyone, there exists another element in your group such that when you dot them together, the result is the identity element. Do you see what I mean? So this is interesting, but let me explain in with numbers. You'll get it right away. So for example, let's say addition 5. Let's say numbers, not group theory but numbers. So 5 plus minus 5 equals to 0. What is 0? 0 is the identity element of the addition. So what about 6? 6, is there a number such that you added to 6 equals to the identity element of addition? Yes. And that number is negative 6. 6 plus negative 6 equals to 0. And so on for any number. So there exists, so we call the inverse element. So for any element in a group, there exists another element that is the inverse of that element, meaning that when you apply the operation of them together, the result is the identity element. So it's similar to with regards to arithmetics. It's similar to the negative numbers and positive numbers with respect to addition. The identity element is 0. And if with respect to multiplication, then that case is a fraction, the inverse. For example, 5 multiplied by 1 over 5 equals to 1, and 1 is the identity element for multiplication. And same thing for 6 multiplied by 1 over 6 equals to 1, and 1 is the identity element. So same thing here with the groups. So if you have an operation that satisfies these four things, then what you have is a group. Remember, the group is a set and operation defined on the binary operation for the element in a set. Now at this point you might be wondering, so what is this operation? Where is my group? Like what is an example? I mean, this is, so, and the answer to that is anything. You just start to create a group. You can do anything you want. Think of this. So I have, let's say I'm going to create a group. So I have 3 balls. My group is 3 balls, and then you need a binary operation. You need to know, this dot this equals to what, which one will equal to this one dot this will equal to what, this dot it dot this will equal to what. You have to define it yourself. Since we got balls, you just define it yourself. Let's say this is ABC. So let's say this is ABC. We abstracted, so forget about balls. We just have A and B and C. So you define it any way you want. So you have so let's create a group. Let's say we have the set is and we need to define a binary operation. Dot, okay. Now we need to define a function. Now let's use a function notation. So let's say f a b equals to equals to what? It's up to you, because you need to, the group definition does not tell you what your binary operation, what it should return. It only says that it must satisfy these. So you just anything you want. Let's say that AB. So AB, you okay. AB, let's say ABA equals to A. Let's say BA equals to A. Let's say AC equals to B. Okay, let's just say that. Let's say CA equals to B. Okay, and let's say ABC. So we need to do CB. So CB. Let's say there it is. So we defined our operation. It covers all possible combinations of two elements in a group. And the result can be anything. I mean, you define the function. So once we have that, now we need to check if our thing now satisfy the group definition. So we check closure for all a b in G. The result of the operation is also in G. Is that true? Check. True, because all the result is ABC. True. Associativity. A dot B. Well, you have to check. I don't know if it's true or not. So you start try to write a Python program or Ruby or Golang. Yeah, learn Golang. Golang is my favorite language, and cause suddenly Golang. Go to my Golang tutorial and learn a new language, Golang. And you try to see if this is satisfy the associativity property of the group. Then you need to check identity. You want to know, and so on. So that is it, folks. That is group theory. But okay, so but what else? But I mean, we haven't covered. We haven't covered. You know. But anyway, so I think that's it for me for me to talk about this, because group theory, it's one of my favorite math subject. And by the way, it's also very deep. I mean, by that I mean you can specialize in group theory. First of all, group theory is the most fundamental part of math. Every mathematician, it's like the alphabet for English. Every mathematician must know group theory to begin with. You know, like you basically, it's taught in it's part of the first course of algebra, and the first course of algebra is taught in the third year in universities for math majors. So if you are a math major, the third year of university, you'll take the first course on algebras. Usually it's called algebra. I mean, yeah. And in algebra, usually the first chapter or the first few chapters will be group theory. Okay, so every mathematician, that's so basic, fundamental. Every mathematician must know it. But also know that group theory also a deep subject. So you can be a specialized, you can be a mathematician, in PhD or post PhD, specialized studying group theory by itself. That is just these things that we just covered. I mean, it's so simple. And also, let me mention, if you go to Xali math, Xali, okay, search for Xali wallpaper groups, and you can find this article. Now, and go to the top, introduction. This I wrote this back in 1997, and it's hugely popular. it's been cited in academia, in professors, in slideshows. They used to write to me for permission to use some of the material. But anyway, this article talk about the discontinuous groups of rotation and translation in the plane. So from this article, you can get a concrete idea of how group theory works. Um, the subject is wallpaper groups. There's a subject called wallpaper groups. It's also in Wikipedia, by the way. If you just search for wallpaper groups. Um, so anyway, that's my intro to group theory. So let me read the comments. So does the inverse rule imply that a group of one is impossible? Group of one? No, it's possible. I mean, because all you have to do is that element multiplied by that itself equals to an identity element. So let's say we have a group and the only element is C. Let's say E. Okay, maybe E is, yeah. So we define a binary operation. So we define E times E equals to E. Okay, so does that satisfy the inverse? Yes, because we have an element. For the inverse rule says for every element there exists another element called inverse, such that when they combine, they returns the identity element. So this is true for every element. We only have one element. So E is E, and E is also the identity because E is E. Yeah, so that's satisfied. I think zero model plus. I got the input. Thank you for the shows. Thank you, Allow. Do you have a RSS notification? Not for YouTube, not for the talk show though. But if you go to any of my blogs, there's a RSS link you can click. For example, let's go to math. Any one of the, for example, my homepage, this RSS, you can subscribe. Yeah, so maybe I should do, I don't know if YouTube provide RSS. I think it does. So you have to look. Yeah, I'm not sure offhand. I think it does. Web feed for subscribers. You have to, yeah. If you search, I think it's there. Maybe I should be my. I think you. I think you should be able to define a group using lambda calculus. Yeah, you can. They are kind of unrelated. I mean, they don't mesh. You just need a simple function. Cool. So great. Thank you, guys. I had a great time talking about the subject I love, and it's actually the first time I kind of taught. I mean, teaching people group theory. Uh, you know. Wait. God, I look at my email. So what am I? Oh shit! I don't know what shit I showed in my email. Anyway, so what? Yeah. Okay. 1 hour and 13 minutes. So thank you guys for coming, and see you next time. Bye.